Okay, so good afternoon. Welcome to my talk. So today I'm going to introduce SODA, an online detection framework for smart contract. So basically today I'll talk about a framework. So it's maybe a little bit different from previous talk. So speaker's work. And also I will try to demonstrate of the ability of being easily extended to support smart contract vulnerability detection. Okay, great. So next, I will quickly talk about the motivation or work. So I think you guys already know, right? Because many speakers already mentioned the importance of smart contract security, right? Okay. Anyway, so you guys know, right? So blockchain have occurred in practice. So here are some examples. And for example, the famous DOR attack and around $70 million was stolen due to a relentless attacks. So those attacks actually are caused by a combination of a technical flaw in designing and implementing software, but particularly, right, so smart contract here. And there are a huge number of smart contracts actually deployed onto the blockchains, and many of them actually are valuable. And for example, the most valuable smart contract holds about 1.8 million ethers. So roughly like a $7 billion. I think this is the number just like a years ago. So I'm pretty sure, right? So this number already increased, significantly. So definitely there are potential like victims, right, for the attack. So as a smart contract. Okay, so the existing approaches can be divided into offline approach and the online approaches. So offline approach basically try to discover vulnerability and also detect the malicious smart contract by analyzing their code. But unfortunately, so cannot guarantee that all the problem can be detected and also removed. So how about the online approach? Online approach basically detects and prevent attacks after contract deployment. Can be further divided into two categories. So category one, try to insert the code into smart contract. But unfortunately, is limited by the size of the smart contract and also the gas mechanism. Okay, so second category, category two, insert the code into a runtime environment. Okay, for example, like an EVM. Unfortunately, also can be not easily extended to detect the new attacks. And also the lacks detailed design, implementation, and evaluations, and also as a time consuming, resource consuming, and also could miss many attacks. I just want to note, so basically, so offline and online approaches, right, none of them is perfect. So basically, they complement with each other. So in our work, we try to design, develop, an online framework, so which can be easily extended to support, so detecting new attacks. Okay, great. So next, I would like to quickly describe the design and the implementation of our framework, SODA. Okay, so this figure here shows the architecture of SODA. Okay, so SODA, as I mentioned, generic online detection framework for smart contract. So it should be integrated into a full node. So SODA actually consists of three major components, including manager, and the information collector, and the log, and that supports various detection apps. So each app, so for detecting one specific problem, and so attack. So I will discuss each component in more detail later. Okay, great. So next I will quickly talk about the advantage of SODA. As I mentioned, right, so we really want to come out so online detection framework, but the framework can be easily extended to support so detecting new attacks. So first major advantage is the extensibility. So this framework can be easily extended to support securing or detecting new problems. And also SODA actually has a lower overhead and also lower detection latency. And also SODA is compatible with any blockchains which adopts so EVM. Okay, great. So as I mentioned, right, so SODA consists of three major modules, and including manager, log, and information collect. So next I will quickly talk about them in more details. So the manager actually is responsible for registering and unregistering so detection apps. So SODA provides two APIs, register app to dynamically registered and unregistered detection apps. So what does the dynamic mean? Dynamic means so a phone node does not need to stop and restart. Okay, so when registering, so a detection app will send the string information to the manager, so including which runtime information is needed, and also the block number indicating when the app should be launched, and also the functions to retrieve, so different runtime information. Log raises a warning if a detection app so detect an anomaly. So the warning includes the following information: runtime information required by the app, and also the hash of the external transaction that checks the anomaly, and also the number of the block containing such external transaction. Okay, so information collector, so collects real-time information, and also it consists so 4 sub-module, including block collector and the transaction collector, instruction collector, and finally information abstract layer. For block collect, so collects all the fields of each block, and the transaction collects all fields of each external and internal transactions. Instruction collector collects the runtime information of each executed instruction. And finally, information abstract layer abstracts, so 11 structured information based on the runtime information collected by above 3 collectors. But there's a technical challenges, but how to ensure the collected information is complete? Otherwise, we may not have a chance, right, to implement some new detection apps. So our idea is very simple, and to record all the effects that can be made by each instruction. So for example, the instruction, so collect will record original balance and also the new balance if an instruction, so changes the balance of an account. We also implement and propose and implement on-demand information retrieval. And on-demand information retrieval, so collects the exact information needed by a detection app, and however ignore the information that is not needed by detection app. So as such, will further reduce the runtime overhead. But how to implement on-demand information retrieval? So our solution as app detection app inform the manager about what runtime information is needed. So then the manager forwards such information to the information collector. Okay, so as I mentioned, right, so information collector actually has 4 sub-modules, including a block collector, transaction collector, instruction collector, and information abstract layer. So those 3 collectors will collect all the runtime information. But then all the collected runtime information will be forwarded to information abstract layer. Information abstract layer will abstract 11 structured information to facilitate app implementation. So those 11 structured information include the contract bytecode, contract invocation, static access, memory access, storage access, and the ether transfer, balance changer, and the control flow transfer, and also in comparison arithmetical operation, and finally event. So afterwards, runtime information is sent to a queue, and the detection app consumes the information asynchronously. Since the asynchronous model is used here, so detection app are analyzing a transaction, and in the meantime, so the phone node will continue to process sequent transactions. As such, so the overhead also can be further so reduced. Okay, great. So next I will introduce so 8 detection apps implemented on Soda. So I'll start with the first one. So number 1 detects malicious reentries attack. So everybody knows, right? So how the reentries attack works. So reentries means caller calls back to the caller. However, so reentries does not mean this is a cyber attack, right? So we consider a reentries malicious. So if there's an ether stolen from a smart contract, so the consequence of reentries attack is a ether loss. So this is a okay, so simplify the scenario of a DOR attack. Okay, so if you look at the, this figure, right, so you can see there's a reentry attack, right, and also you can see steps 3 and 4 form a circle. Okay, so from this example, you can see, okay, Ether actually has stolen, right, from the victim during reentry attack. So this detection app needs transaction information, including sender, receiver, and the Ether information. Okay, so second, the detection app detects, okay, unexpected function invocation. Unexpected means, okay, unexpected function is not implemented in a smart contract. So as a result, so the fallback function is invoked instead, right? So the consequence for this kind of problem is unexpected result. So like a token stealing. So this detection app needs contract bytecode and the contract invocation information. Detection app 3 detects function invocation with an invalid input. So invalid input data means, okay, the length of the input actually is shorter than expected, okay, so, and the correct length. So the consequence for this kind of problem is also is unexpected result. So for example, the famous, okay, short address attack, so for stealing token. So this detection app needs a contract invocation information. Okay, so detection app 4 detects function invocation bypassing the incorrect permission check. So permission check is required for some sensitive operations. For example, like send the Ether and also change the contract owner. Okay, so in reality, message sender should be checked rather than the transaction dot origin, the global variable, right? If you are using transaction dot origin for authorization, could make, okay, a contract, right, vulnerable. Okay, so the authorized account calls into a malicious contract. So the consequence is, okay, phishing attack can bypass the check of transaction dot origin. So this detection app needs contract invocation information and the runtime information of transaction dot origin and also so the equal, okay, operate. So detection app 5 detect the failed transaction invocation whose return value is not checked. So the consequence is very simple. So basically, it's an unexpected result since the caller does not know, right? It's a failure. So this detection app needs a contract bytecode and the contract invocation information. So detection app 6 detects, okay, invocation of a standard information, standard function without emitting a standard event. So for example, the ERC20, the most popular token standard, so requires, okay, so 2 functions, including transfer and transfer from, must emit the transfer event. Okay, so if those 2 functions do not emit, okay, so transfer event, so some third-party tools cannot observe the token transfer, right? So as a result, fake deposit attack could occur. So this detection app needs contract invocation and the event information. So detection app 7 detect invocation triggering Strucker balance check. So this is just one example, right? So Strucker balance check. So if the balance is equal to 1 Ether, but unfortunately, Strucker balance checker, right, can be easily, okay, so disturbed by the contract, okay, so self-destruction. Okay, so consequence definitely, right? So the program logic is broken. Okay, so this detection app needs runtime information of a balance and also equal operate. So the last detection app implemented on Soda and detects invocation, triggering block number and time step dependency. Block number time step dependency, okay, means control flow depending on the block number and okay, so time step. But unfortunately, so block number and also time step, right, is set by a miner. So in this case, a malicious miner is able to change the program logic and also the program execution, right? So this detection app needs runtime information of block number, time step, and also comparison information. Okay, so next I would like to present the evaluation result of Soda. So we will evaluate the effectiveness of Soda, and in particular, So we have done extensive experiment to answer a couple of research questions, total 6 research questions. So the first research question: can SODA be easily integrated into any EVM compatible blockchains? So we first implemented SODA in Ethereum using 2,200 lines of code, and then we migrated this implementation to 2 more blockchains, including Expanse and Wenchain, using just 27 and 164 lines of code. So the answer to the first research question: so SODA can be easily integrated into EVM compatible blockchains. Okay, so the second research question is: can SODA facilitate the development of detection apps? So the figure here shows the line of the line of codes for each detection app. So the code amount for each detection app ranges from 53 lines of code to 201 lines of code. So the answer to second research question: SODA can facilitate the development of detection apps. Okay, so the third research question is: what is the overhead of SODA? Okay, to evaluate the overhead of SODA, so we will do 2 different scenarios. First, running SODA with 8 detection apps to analyze historical transactions. So results are shown in this figure here. So you can see the overhead of SODA, right? So analyzing the historical transaction is lower. And also it can be observed actually the overhead of data collection, right? Data transmission dominates, you can see. Okay, so the second run SODA, so with 8 detection apps to analyze new transactions. And we can see actually, so the overhead is negligible. So the reason is block mining is obviously more time consuming than SODA. So the answer to the third research question: so overhead is lower when processing historical transactions and is negligible when processing new transactions. Okay, so research question 4: can on-demand information retrieval reduce the overhead of SODA? So to demonstrate such ability, so we designed a special app called Tracer. So basically, Tracer takes in all the information, but then return immediately. So we consider this as a kind of we turned off the so on-demand information retrieval. So it's equal to like turning off the on-demand information retrieval. So then the result is shown here. Okay, so basically, so Tracer actually incurs 34% of the overhead, and definitely, right? So this is 1.3 times higher than SODA plus 8 detection apps. So the answer to research question 4: on-demand information retrieval effective in reducing the overhead of SODA. Okay, so next one is research question: what is the detection latency? Okay, detection latency exists because detection app run asynchronously. So the analysis of a transaction falls behind the execution of the transaction. Okay, cool. So the results are showing in this table. So you can see, so the detection latency for each app ranges from 1 microsecond to 10 microseconds. So 8 detection apps incur total 35 microseconds. So the answer to the research question 5: so detection latency is also negligible. Okay, so the last research question, is: can SODA easily integrate third-party tools? As I mentioned, we propose an online detection framework. We try to emphasize the extensibility. So last one also we want to take a look at whether we are able to integrate some third-party tools. So to demonstrate such ability, so we integrate the 3 tools, including MedMax, so EVM bytecode, decompiler, OSIRIS, by designing 3 apps. Okay, so each app only needs 75 lines of code, and why? Because it needs contract bytecode and also needed to invoke the third parties. So the answer to the research question 6: SODA can be easily extended by integrating third-party tools within it. Okay, so then I will quickly present result of running, okay, so 8 detection apps on 3 blockchains. Okay, so this table here presents the statistics of 3 blockchains. So when we deploy SODA onto them. So for example, for Ethereum, so more than 8 million blocks and 500 million external transactions and 70 million smart contracts are analyzed. So next, let's quickly take a look at detection result for those detection apps. First, let's take a look at detection app 1. So detecting Ranger's attack. So we found 31 vulnerable smart contract, and the number after vertical bar means 24 actually are open source smart contract. And also we found nearly 2,000 attacking transactions. However, here we have challenges. There's no ground truth data set, right? So available for evaluating smart contract vulnerability detection tools. There's no such kind of ground truth data set. So all solution, all ground truth is based on manual analysis and plus random sampling. If let's take a look at the detection app 1 as an example here, right? If we only detect a small number of vulnerable or problematic smart contracts, so then we'll manually analyze all the detected smart contracts. However, let's take a look at the other detection apps, right? For example, PIF detection app 4, we found a larger number of problematic smart contracts. So then we'll randomly choose some of them, and then we manually analyze all of them, which means everything is based on ground truth is based on manual analysis, because there's no such kind of ground truth data set available today for evaluating smart contract vulnerability detection tools. So we have to use all ground truth is based on manual analysis plus random. Cool. I think finally I will conclude my talk. So in my talk today, so I propose online detection framework. So we try to emphasize 3 main advantages. So including extensibility, efficient, and compatibility. And we also implemented 8 detection apps on the proposed framework. And the source code and also experimental result are released. So in our GitHub, feel free to download, give it a try. And finally, I want to talk about some future works. So of course, right, we try to further improve the propose the online framework, and also we try to design develop more detection apps to demonstrate the extensibility of the proposed framework. And also we try to apply SODA in the other domains, for example, blockchain, so profiling, and also want to further extend the SODA to online applications. Thank you for listening. Any questions? Sorry, I speak a little bit over time. Sorry.
Where we started slightly late, so sorry. A question or two? Or? Muli?
Can you detect the Nomad bridge attack?
We haven't tried. But as I mentioned, we'll further design develop more attacks. So detection apps. But that's why we try to propose an online detection framework, right? Can be easily extended to develop new detection apps for detecting new attacks. Thank you.
I have one small question. The target audience for SODA is, I understood it was used by you and your group, but does it have a wider target audience for use?
Yeah, so basically, you can think about it, even in my class, I try to use SODA as a teaching material. So if we identify new attackers, right, so we can simply ask my students, hey, so can you develop a new detection app, see whether this problem can be detected?
Thank you very much. You have one question? No? Okay, so it's time for the break.
Yeah, sorry, I speak a little bit over time. So I didn't control time very well.
Thank you.